Move on to our next speaker. As I mentioned, Margaret is a farm advisor up in Yolo County, and she's been doing a lot of fantastic research on cover crops and soil organic matter and nitrogen made available for plant growth. And so Margaret today is going to talk to us about nitrogen made available from cover crops. So Margaret.
Great, thank you, Richard. Okay. How does that look?
Looks great.
Okay, thank you. Thank you, Richard, Joji, and everyone for putting this workshop together. It's really a pleasure to be here with all of you. I wish we could all be in person, but we'll have to save that type of fun for another workshop, another year. As Richard said, I'm the Small Farms Advisor for Yolo, Solano, and Sacramento counties, and I have the unique privilege to have a program assignment focused on organic production. So today I'll be talking about cover crops and crop residue in the nitrogen budget. And my goal is to help build your ability to understand and estimate the contributions of crop residue to the nitrogen budget. So whether this is for nitrogen planning, reporting, decision-making when selecting a cover crop, or terminating or timing of activities, I hope this information can provide you with some new and useful ways to navigate those scenarios. This here is a conceptual figure. Oh, wait, can you see it, or is it blank?
We can see it.
Okay, sorry. This here is a conceptual figure that we designed using data from multiple studies from the Geisler lab to illustrate the relative contributions of the multiple nitrogen sources in a summer growing scenario in Yolo County. And as organic farmers, the contributions from many sources is an important one to really grasp and think about how much nitrogen is coming from all of them, because it's really a collective contribution. And sometimes it can be framed that we think more about our amendments as being our nitrogen sources, when really it's many actions accumulating over time. So on the bottom here, we have the soil and the soil organic matter. So a lot about what Daniel just introduced. In this light green band, we have cover crops or crop residue. In this blue band, we have, this represents a compost application of poultry manure. This purple band is a granular fertilizer at 4%. And on top, we have this orange band, which represents some nitrogen coming from the irrigation water. And this red dashed line is just to represent a tomato, a fresh market type tomato, an uptake curve for how much nitrogen it's using over the season. So I have this here just to give the idea of all of these contributions from many places are really building the nitrogen program in an organic system. Now on the coast, the ratio of contributions is likely similar, but with the coastal climate, the summer peak may be less pronounced. And so that nitrogen release and uptake is likely more spread out across more months. So the amount of nitrogen made available from crop residues largely depends on the biomass of the residue. So how much material is out there, the nitrogen content of those residues, and this C to N ratio and total nitrogen content, which is a lot of what Daniel just introduced. And then these factors that are driving and influencing the microbial activity, soil moisture, and whether that material was incorporated or left on the surface. So I'll be going through each of these and discussing how the quantity quality affects the availability. So first I'll talk about the biomass of the residues. And the vast majority of nitrogen in cover crops is in that biomass, that above ground biomass. If you're ever asked how much nitrogen or nitrate is coming from your cover crop, at a minimum, you'll need to know two pieces of information, and that's the biomass and the tissue and content. So the first step is getting an idea of this biomass and what drives the production of the biomass. Can you look at this picture and get an idea of how much biomass is out there? This picture is just under 3 tons per acre dry weight of cover crop residue. Here's another image. So we have in the foreground or in the middle here, a vetch cover crop. This represents 2 tons per acre of biomass. So when during the season is biomass accumulating? Here's a figure showing the growth of a cereal crop. So some cover crops are cereal, some are legumes. So in the case of cereal crops, after the boot stage, so right about here, the rye cover crops can double in biomass with little additional N. So they're really putting on the bulk of the biomass in the latter half of their growth stage. So shortly after boot stage, most of the N movement is in the translocation, and the rate of N uptake decreases significantly. So this curve shows the biomass accumulation over time. And so what you can see is right about here, we just passed boot stage, and we see this rapid biomass accumulation, this buildup of biomass. So when thinking about getting more nitrogen into our fields, we're doing that more quickly after this boot stage. Now, to achieve this growth, cereal crops, the non-legumes, scavenge for residual nitrogen in the soil. The grasses in particular have these deep, efficient root systems, and they scavenge for residual nitrogen in the soil profile. And they have good potential to capture plant available nitrate that is in the soil, preventing it from leaching into subsurface groundwater or running off with surface water. So that's one of the advantages. However, they will be limited by the available N in the soil. So these two lines represent a scenario in which there was sufficient nitrogen in the soil, high amounts of residual soil nitrogen, nitrate, and a scenario where there were lower nitrate levels. And so you can see how that influences the potential for the biomass accumulation. In the document that Daniel was talking about, which we will share in the link, we have a lot of the tables that we'll be talking about throughout this workshop. So this is one of the tables in which we have listed out a sort of some baseline common estimates for the amount of cover crop biomass from some common cereal, legume, brassica cover crops. Just to at least give that baseline idea. But refining the biomass production on your farm has to come with some amount of sampling and training your eye to be able to gauge what 2 tons, 3 tons, 4 tons of biomass looks like. But you can see here how if we just look at oats and rye, they're the highest biomass producers, whereas the vetch only type species are the lowest. And the mixes with some cereal, legumes, bell beans, mustards are in this intermediate range. Now thinking about legumes. So the vast majority of N in the cover crop is in the above ground biomass. And this is regardless of whether the nitrogen is coming from residual soil nitrate, in the soil, or if it's fixed from the atmosphere by the bacteria in legume roots. So legume, as many of you know, the legumes differ from grasses and other non-legumes in their ability to form symbiotic associations with root nodulating bacteria called rhizobia. And this symbiotic relationship provides, the plants are providing the root nodulating rhizobia bacteria with the carbohydrates, and in exchange, the rhizobia are providing nitrogen. And this exchange is not free. The legumes can invest as much as 20% of their net photosynthate production to supporting those rhizobia. And the rhizobia share nitrogen that they could otherwise be using for self-growth and reproduction. And this exchange occurs in those roots. However, that nitrogen is translocated to the above ground plant growth for the most part. And to give you an example, in a hairy vetch and Austrian pea cover crop that was 100 pounds of nitrogen per acre in the above ground biomass, the roots had about 10 pounds of nitrogen per acre. And when you also look at the makeup of those roots, they had a tissue content of less than 2% nitrogen and a C to N ratio of more than 20:1. So the plant available nitrogen, the PAN, that release was close to 0. So in that example of a hairy vetch Austrian pea cover crop of 100 pounds of nitrogen per acre, that nitrogen was coming from the above ground biomass and not from the roots that are left in the ground. So legumes, this ability to take the atmospheric N means that they're providing a net input of N to the soil when they're incorporated. One feature of a legume cover crop is that they typically have higher N content in their tissue. And they will usually accumulate N longer in the spring than non-legume cover crops. So thinking about the timing and which scenario best fits into your planting windows. And whether an earlier accumulating, a crop that accumulates biomass earlier in the season or later in the season, these can be selected based on the crop species. So now thinking about when is nitrogen highest? So we just spoke about biomass accumulation. Now thinking about nitrogen. So I discussed how after boot stage is when that biomass really accumulates. However, it's at boot stage that the leaf tissue N content is highest. So when we see what that curve looks like, this curve is showing the percent nitrogen. And so we see it highest earlier in the season, right before boot stage, and then it starts to decline. So that's the other piece of information, is understanding this tissue N content. And building on the table we looked at earlier, we can see our top 2 candidates here as a cereal cover crop, that the tissue N content is less than 2%. And as we scroll down, these vetches are among the highest at 3.5, 4.5 or so percent tissue N content. And again, these mustard, bell beans, and mixes are intermediate. So you can see the sort of decision and challenge here in choosing biomass and tissue N content. Because so then when we think about termination, we think about how do we maximize biomass and maximize tissue N content. And so identifying that point in the season can help with some termination decisions if there's flexibility in that decision moment. So here we can see the biomass accumulating, the nitrogen content decreasing, and terminating somewhere in here is going to maximize our total N. So that's going to be the tissue content times the biomass. The legume cereal cover crop mixes are one way to sort of capture the qualities of both a cereal crop and a legume crop. They can provide this robust system with the capacity to both scavenge the residual soil N, but also utilize atmospheric N and grow abundantly even in low N conditions. And then this can often lower a total, the tissue N content can be higher when legumes are mixed into a cereal crop. So when we look at the N content of residues, a couple of things are influencing that. It tends to be the cover crop age. So the younger the cover crop, the higher the N content of that species, and the higher the N availability following incorporation. So they're going to tend to also have a lower C to N ratio, be more available, and so that's why they'll be available earlier than older materials with a higher tissue and higher C to N ratio. In general, the legumes and mustards have that higher N content in their tissues, more than 2%, and that's what will allow for this rapid mineralization. Now, cereals can have higher N content, but that's going to be earlier in their growth period when it will be more than 2%. So that's when they're juvenile, and they will have less biomass. So that's the trade-off. So now we've talked about the biomass, the tissue N content, but only a portion of that total N becomes available to the following crop. And so how much becomes available? So the C to N ratio is the mass of the carbon relative to the mass of nitrogen in a substance. And the soil microorganisms have a C to N ratio near 8:1. They must acquire enough carbon and nitrogen from the environment in which they live to maintain the ratio of carbon and nitrogen in their bodies. And because soil microorganisms burn carbon as a source of energy, not all of the carbon that a microorganism consumes remains in its body. A certain amount is lost to CO2 during respiration. And so to acquire the carbon and nitrogen a soil microorganism needs to stay alive, it needs a diet with a C to N ratio near 24:1. So that's where we often talk about these numbers above and below 24:1, as Daniel pointed out earlier. And so when carbon contributions are high, these decomposer microbes will scavenge any free nitrogen in the soil or immobilize it in their bodies as they chew through high carbon materials. Vegetable crop residues typically have a C to N ratio below 15:1, which allows for rapid nitrogen mineralization to begin immediately following incorporation into moist soils. Whereas residues with a ratio of 15:20, as is common with cover crops, those are going to mineralize a little bit more slowly. And then those above 20:1 will be very slow or start to tie up and immobilize some of the nitrogen. And we'll look at that a little bit more closely in a minute. So here are some figures of cover crops and their carbon to nitrogen ratio. So in this first field, this is a wheat crop. The second field is a vetch crop and a veg crop. This fourth field is a mix, and we have a few mixes here, mix field 4, 5, and 6, and 7. And just to give you a sense of what the range, so here we have a range of 12:1 to 18:1 of the cover crop carbon to nitrogen ratio. For contrast, here you can see a very mature cover crop. It has a lot more biomass, but you can see the seed heads and the flowers, and that cover crop is measuring 32:1. And here's the tissue content of those same fields. So you can see this higher C to N ratio has a lower N tissue content, 2.7%. Whereas when we go over here to the 12:1 C to N ratio, there's 3.9% tissue content of nitrogen. So you can see how those two things are related. And then when we revisit the figure that Daniel introduced, we can look at what percent of that tissue might be mineralized based on tissue content. And we'll go through this exercise in a minute. So we look at the tissue N content, the total N in the biomass, and then visiting this figure, I'm going to estimate what that mineralization rate might be. So let's walk through this first one together. I have 1.7%, so that's going to be in this less than 2% band. And so if I draw this line over, I said that it had an estimated mineralization rate of 10%. And then let's do this last one at 4.7% tissue N content. That's going to be up here somewhere. Draw this line over, and I put in it had a 55% mineralization rate. So then to estimate what amount of plant available nitrogen of all the total nitrogen in that cover crop, you'll multiply the biomass times the mineralization rate to get available N. So in this Cayuse oats example, we might expect 13 pounds of nitrogen per acre after that cover crop is incorporated. Whereas in this Lana woolly pod vetch example, we might expect 100 pounds of nitrogen post-incorporation. So in that way, you can get your own numbers and do these types of calculations paired with a figure like this to estimate mineralization. Cover crop residue is going to function similarly to cover crops. And so we can talk about them in the same way and think about them in the same way. Similarly, we want to have that information of C to N ratio or tissue N content. And most of the tissue N content of vegetable residue is going to be 2.5 to 5%. So it's going to be somewhat similar to a leguminous cover crop. And then if you have idea of how much residue you have in the field, you can do that calculation. We have included in that document we've been referencing a table with some estimates of residue. So if we take broccoli, which tends to can have tremendous amounts of residue, especially on the coast where that is prime broccoli growing conditions. And so this is an example yield of 10 tons per acre, and how much N content is in that tissue, or 68% of the total N that was put into that crop still remains in that residue. That's a lot of leftover nitrogen. So then the expected amount of nitrogen in that residue is going to be 240 pounds. So that's the total nitrogen in all that residue. At that point, you would want to do that calculation that we just did here and walk through 240 pounds times a mineralization rate that you choose based on your estimate. So maybe 3% nitrogen in a broccoli residue. And you can get what a actual plant available nitrogen release might be from that residue. I have this picture here to illustrate the concept that only a portion of all this material that we put in is going to be used by the subsequent crop. So this was work by Louise Jackson, who is here today, who will be talking next. And this is some work in which she tracked how much of the nitrogen from a cover crop was taken up by a subsequent lettuce crop. And what you can see here is that this is just the first planting of lettuce. There were 2 plantings. But in this first planting, combining the shoots and the roots, just over 20% of that lettuce's total N came directly from the cover crop. And where did the rest of that cover crop nitrogen go? A lot of it went into the soil organic nitrogen, which is what Daniel was talking about. A small amount remains tied up in the microbial biomass. This section here describes what would have been potentially leached. So I just have this here to further demonstrate or illustrate this idea that our crops are only taking up some amount of the nitrogen from these cover crops or crop residues following incorporation. And a lot of it is being built into the soil. And that's where we get this tremendous ongoing background release of N in organic systems, where we're repeatedly cover cropping, putting crop residues in, adding materials like compost. We build this robust background nitrogen source in our soil. And just to reiterate, what's going to influence how much of that nitrogen we actually get. So in addition to the basic factors of biomass, tissue content, C to N ratio, we have to consider the microbial conditions. So soil moisture is essential for them to do their work. And so that's going to be a driver of what we actually get to see from the microbes. And whether those residues are left on the surface or incorporated. And Daniel touched on this already. But basically, the surface applied residues will decay more slowly than the incorporated residues. So that can be ideal. That can be maybe a strategy that was mentioned before. This idea of maybe leaving broccoli on the surface to delay leaching, or it can be incorporated into a system. So lastly, I encourage folks to try to get some of these numbers for yourself. And I think that doing this exercise of collecting biomass and measuring the C to N ratio and the nitrogen content of that biomass is an important way to begin training your eye to understanding how much is going back into the system and what practices are you doing that are influencing the quality and quantity of that material. And it's quite simple and cheap to do that. So quickly here, I'll give you a demonstration of that. Basically, we have this meter square, which is just a set of PVC pipes measured out to 3 feet by 3 feet or meter by meter, whichever you prefer, but a set area. And you take all that cover crop, you cut it down, take all that material or crop residue of vegetable residue, and you dry it. And then a subsample of that is sent to a lab to get those, the tissue N content and the C to N ratio, and those tend to be under $20, $11, $12, $13, $15. So it's quite cheap. And in this way, you can get real numbers for your field. And after this is done a few times, I believe that you'll be able to train your eye to begin to read what might be going on out there. So you'll be able to plug in your own numbers for tissue N content and cover crop biomass. And then you can use the information that we have provided to get your estimated plant available nitrogen. So in summary, the amount of cover crop N that is made available for vegetable crop growth varies widely, and estimates range from 0 to about 50%. So the unmineralized N from that crop residue and the cover crops contribute to the total N in that soil organic matter and the long-term soil fertility, but is less available in the short term. So some food for thought. The cover crop mixes with a higher proportion of legumes, particularly when terminated before flowering, will release more of their N than later terminated crops and grass-heavy mixes. So I apologize, I didn't quite emphasize that in the legume growth, I talked more about the cereal growth, but in the legume growth, the tissue N content is maximized just before flowering or early flower. So that's where that curve will start to decrease for the legumes. In early spring kill of cereal grains, reduces accumulation of carbon more than nitrogen. So the rate of release of the cover crop N into the following crops is faster. In a cover crop mix, low residual soil N will limit cereal growth and promote legume growth. A wet winter will encourage more rapid cover crop decomposition, which will lead to earlier availability and higher availability of early nitrogen. So we have to keep thinking about every year's conditions and putting it all together. So the C to N ratio and the tissue N content are good predictors of this plant available N. The younger the crops, the higher the N content of that species, the higher the availability following incorporation. And the legumes and mustards are going to have a higher tissue N content than cereals. The grasses will scavenge N, keeping N in the system, reducing the loss from leaching. And more biomass leads to more total N contribution. Not necessarily plant available, but just more total N contribution. And the soil moisture is going to be a driver for when and how much decomposition occurs. And whether it's incorporated or surface mulch will also influence when and how much decomposition occurs. I have a couple of resources, and I'll put these in the link in the chat. So this is just looking at doing some nitrogen calculations using your own biomass and tissue N content numbers. Here's this cover crop chart goes through, is created by the NRCS, and it's a guide to the characteristics and biomass and N expectations of many cover crops in California. And that's it. So thank you for your attention. And if we want to answer any questions, we might have a few minutes.